Okay, good morning all. I hope I'm audible. Can anyone please confirm?
Yes, sir.
Yes, sir, you are audible.
Okay, thank you. Before we start the session, all of you go to the second chapter, open that same DLI course link and click on the second chapter, that is Managing Accelerated Application Memory with CUDA C++, Unified Memory and NSYS. Right? You click on that and start that cloud instance. Right? It will take 4 to 5 minutes to start that instance. So make sure before we start the session, you can start that launching process. Let's wait for 2 more minutes and then we will start. By the way, how many of you tried for the completed the first chapter with advanced topics also? Raise your hands. Nobody tried for the assignment or exercise problems from chapter 1? Okay, only one. Fine, you have to try for all the exercises problems, so to practice, right? Because if you limit only topics that I'll be covering, then it may be difficult for you to remember and practice as well, right? So every chapter we have some exercise problems as well as some uh, final exercise or maybe some advanced topics are there that you are supposed to attempt, right? So it will give you a good practice also, and it will make you to understand the concept in better way. Fine. So let's start with this today's chapter, that is unified memory. Before we start with this hands-on session, I'll just give you a brief idea about what is unified memory using this very small presentation. Okay, so we have already discussed this process in case of C programming and CUDA programming, how we write code. So this is a template. Whenever you write a CUDA program, you declare CPU variables, allocate memory to CPU variables, declare GPU variables, allocate memory to GPU variables, transfer data, initialize the data at CPU memory, and copy data from CPU memory to GPU memory, right? Then seventh step is CPU instruct GPU for parallel execution. That means we are writing GPU code, right? Then copy results back from GPU memory to CPU memory, right? This is the flow of your execution in any CUDA program, right? That is what we follow in case of CUDA C++. But now here, if you see this allocation, the red color indicates here, these are the steps, these are kind of overhead or excess of work for the programmer, right? So allocating memory, CPU variables, declaring GPU variables, etc., we have to perform from step number 2 to 6 by writing explicit function calls, right? And before CUDA's version 6.0, before that 6.0, we have to perform all the steps manually, right? We used to use different functions, right, to allocate memory, different functions to transfer data from CPU to GPU, GPU to CPU, right? So the entire process was manual, right? And that is to increase the size of your or number of lines in your code also, and it's to increase the complexity of your code also, right? So every time, whenever you want to perform any operation on GPU, you are supposed to perform all these 8 steps, right? But out of which now from CUDA 6.0 onwards, these two to six number of steps are automated. That means you don't have to worry about it. And in the previous chapter, we have discussed one function that is called as CUDA malloc managed. That CUDA malloc managed avoid all these steps, right? So you don't have to write explicitly all these steps. The rest of all this data transfer, memory allocation, declaration of GPU variables, everything will be handled by the automated process, right? So here the manual transfer is removed, and now we can perform this automated transfer. What we have to do? First, we have to only declare a variable on CPU side, and we have to allocate memory, and that we have to ensure that that memory will be unified. So what is concept of unified memory? So in this picture, the two scenarios are there. One is without unified memory concept, and with another one is with unified memory concept. So if you see on left hand side, here we are having blue color indicate this is a CPU processor, and a dedicated RAM is available for CPU. Similarly, in this green here, it is showing GPU and its own GPU memory, right? When you write a program, you declare all variables from CPU side, GPU side, you transfer data from CPU memory to GPU memory, GPU will perform computation, and results will be given back to the CPU memory. That is the manual process, right? Before your CUDA 6.0. Nowadays, ideally, it is considered a logical view of memories like this. So there is no difference between CPU memory and GPU memory. Again, it is just a logical view. Practically, if you see at hardware level, both the memories are different, right? But logically, it is giving a picture that we are having only one memory, and that is common for CPU as well as for GPU. Of course, both the hardwares are different, but logical or programmers view is like that. For programmer, there is no difference between CPU memory and the GPU memory, and that's why it is called as unified memory, right? Now how it works? Let's say we are having a CPU code here. Let's say sorting file quick sort program function is there, where we are allocating memory using normally data equal to malloc function, right? Using malloc function here, we are allocating memory here, and then we are maybe reading some input file, and then we are calling this quick sort function, right? So this is your normal CPU code. Now, let's say you want to convert this CPU code into GPU. So here you will just change this data, that is memory allocation using malloc, will be replaced by this CUDA malloc managed, right? So this is the one change we have to perform, and then quick sort function will be converted into parallel version, maybe using some different logic, right? And finally, we are having CUDA device synchronize here. Now here, according to the memory point of view, we just replaced malloc function with CUDA malloc managed. And we are not doing any explicit data transfer from CPU to GPU or GPU to CPU. The data transfer will be automatically taken care by this unified memory concept, right? Again, let's say you want to perform this manual transfer also. It is also possible in the latest CUDA version, right? If let's say there is a specific requirement that you don't want to trust this unified memory, or maybe for better performance you feel that manual transfer is required, that is also possible. But most of the time we are going to refer this CUDA malloc managed, because it will reduce the burden of the CUDA programmers, right? So all the steps to transfer data explicitly from CPU to GPU, GPU to CPU will be removed, and only this CUDA malloc managed will be used. Fine. Now, this unified memory is a single memory address space and accessible from any processor in the system. We are having two processors as of now. One is CPU, other is GPU. Now, you will be declaring only one variable, right? And you will not say whether it is for CPU memory or whether it is for GPU memory. You will just declare it, and you will allocate memory using CUDA malloc managed. And whenever it is required, it will be automatically transferred from CPU to GPU or GPU to CPU. right? Then, when unified memory is first time allocated, it is not yet resident on host or device. Host means CPU and device means GPU, right? This is the term used in CUDA programming, host and device. Host stands for your CPU and device stands for GPU, right? So first time whenever you allocate memory, it will not exactly allocate either on CPU or GPU. You just use the syntax CUDA malloc managed. Though we are saying that CUDA malloc managed allocate memory, but first time when you invoke this CUDA malloc managed, it will not get allocated on CPU or GPU. Right? Next step is when either host or device attempts to access the memory, a page fault will occur. Right? Then at this point, host or device will migrate the needed data in the batches. Right? So to understand this page concept, for those who are not from computer science background, I'll just give you very short idea about what we mean by this pages. Right? To understand this, let's take a simple example here. I hope this text is visible, right? If not, you can zoom in from your screen. Let's say we have an integer array A of size n. So there are n number of elements are stored into this integer array A, right? And n equal to 1000 suppose. Now let's say in my system it takes 4 bytes to store one integer. It takes 4 bytes to store one integer. Now in this case, total amount of memory required to store this entire array A equal to 4 bytes for one integer multiplied by 1000 because we want to store 1000 integers. So 1000 multiplied by 4, it will be 4000 bytes, or we can consider approximately it will be 4 kilobytes, right? So this is how we find out amount of memory that is required to store that specific array, right? Now, if you see main memory where the entire 4 KB is not directly allocated to this array A in contiguous fashion, right? So what operating system does, it divides this entire 4 kilobytes into number of pages, right? Number of pages in the sense number of chunks. So it is not going to store the complete 4 kilobyte in the at one location. It first divides the entire array into number of chunks, and that chunk is referred as page, right? So this 4 bytes of kilobytes of memory will be divided into number of chunks. Let's say the chunk size or page size is 1 kilobyte, then this entire array will be divided into number of pages equal to 4. Right? So this is one simple example how operating system divides the array into number of pages. Right? Let's say I give you another example and you try to answer this. Let's say we are having a floating array, let's say B, and with n elements where n equal to uh, let's say 5000, right? And let's say each float value takes, let's say 8 bytes of memory. Now find out what will be the size of that array, and if page size equal to, let's say 2 KB, find out number of pages. What will be the size of that array? Question is, what will be the size of this array? Yes. Any answers? Okay, so 40 KB or 40,000 bytes or 40 MB. Let's see what is this. So simply what we are supposed to do, we have to take 5000 elements multiplied by 8. right? So how much it is? 40,000 bytes, right? So 40,000 bytes required to store this complete array B, or 40,000 bytes we can approximately consider 40 kilobytes, right? So this is the size of required for entire this storing this array B. Now this entire 40 KB will not be stored at the same you can say contiguous location. It will be divided into number of chunks, right? And here the chunk size is mentioned, that is 2 KB, and it is referred as page size, right? And now we want to find out how many pages in which this entire 40 kilobyte array will be divided into. So here the simple idea is to calculate number of pages. We'll calculate this array size, right? Let's say here we are having 40 KB, right? And each of your page size is 2 KB, right? So how many pages are possible here? 20, right? So that means this array B will be divided into number of pages equal to 20. Again, it is not like that on only array will be divided into pages. Your complete process will be divided into number of pages. I just tried to give you some simple visualization of these pages in your main memory, right? But typically it is not only the data inside your program gets divided into number of pages. Your complete process, when you start executing any program, a process will be created and that complete process will be divided into number of pages, right? So just to understand the paging concept, I tried to give you a simple scenario. Now this much knowledge to understand this unified memory is enough, right? You don't have to go into the details of advanced concepts like a segmented paging, pager segmentation, right? Page table entry. So that is not at all required. We just have to understand the entire memory that is required to execute any program that will be divided into number of pages. That's it. Okay. So that is the meaning here is, now when either host or device attempt to access that memory, a page fault will occur. That means if required memory is not present in that let's say required data is not present in one of the CPU or GPU's memory, then it will generate this page fault error, right? Now, if page fault is there, then it will transfer the data. To understand these statements, let's see this simple example code here. We are having two float type arrays and we have allocated memory using this CUDA malloc managed here. So what is this program is doing? First of all, we are allocating memory. Then we are initializing these arrays x and y. With x, all the values of x are initialized to 1 and all the values of y are initialized to 2. Then we are having this block size and number of blocks, these parameters, and we are launching this add function that to be executed on GPU, right? And just taking arguments like n x comma y. So it is going to perform x plus y, suppose, right? Then we are using CUDA device synchronize. And finally, we are checking whether we are getting the results same or not, or we are calling some CPU side function. So you see this pattern here. We allocated memory using CUDA malloc managed. Now we don't know whether it is allocated on CPU side or GPU side, right? Now first thing what will happen, we allocate this using CUDA malloc managed, but when you we execute this CUDA malloc managed statement, as of now memory will not get allocated either on CPU or GPU, right? I know this is a contradictory statements here. We are calling this function CUDA malloc managed, right? And we are saying for x and y variable, we want to allocate this much amount of memory, that is n into size of float, right? But after execute, first time when you execute this statement, memory never gets allocated on CPU memory or GPU memory as of now, right? Now point is which function we use after this memory management, memory allocation, either CPU side function or GPU side function. That is the important thing to understand where the memory gets allocated first, right? So as of now we just call this CUDA malloc manage function, but memory never gets allocated neither on CPU side or GPU side. Now next thing, we are executing this for loop, right? So this is not a GPU function, this GPU execution, this is CPU execution. A simple for loop is there where we are trying to initialize this X and Y array values, right? So CPU side execution is there. Now what happens when CPU tries to access this X and Y values, it will result into page fault. Page fault means it is trying to access X and Y values, but they're not currently present on the CPU memory, right? Because using this CUDA malloc manage, memory is not allocated yet. Now, first time we are calling this X and Y on CPU side, so page fault will occur and memory gets allocated on the CPU side first time. Right? For X and Y variables, memory gets allocated to CPU side. Right? Now, entire data X and Y residing into the CPU's main memory. Right? I repeat here, when you call CUDA malloc managed, memory never gets allocated. We are just using this function. But next time, whenever the data X and Y is referred, let's say on CPU side, then page fault will occur and CPU side memory gets allocated for both X and Y variables here. Right? How much memory? N into size of float. This much amount of memory gets allocated for X and Y and CPU side. So you can see I'm using this orange color in the host side. That means currently X and Y arrays are allocated on the host side or CPU side. Right? Next, we are calling add function, but this is supposed to be executed on GPU. And this function is using same variables X and Y. But now this GPU function is executing on the GPU side, right? And definitely to perform any operation on X and Y, this X and Y variables values must be transferred to the GPU side, right? GPU directly trying to access is, it will cause page fault. That means GPU is trying to access this X and Y arrays, but X and Y currently present on CPU side, right? But GPU trying to access on the GPU side, right? So when GPU refers these X and Y in its own memory, it will not find out that, right? Because currently X and Y is residing in the host memory. Then whenever it is referring to the location or data that is not present in its own memory, again page fault will occur. And at this point now, the entire data X and Y will be transferred from host memory to device memory, and that will be automatic. Will be having this page migration engine that will help you to transfer this data automatically, right? And then we'll be having this CUDA device synchronized just to ensure that host or your CPU will wait till this add function completes. Now you tell me where this X and Y is residing as of now, whether it is on GPU or CPU till this point when we are executing this CUDA device synchronize. Currently, whether data X and Y values are on host side or device side. After executing this add function, tell me whether X and Y values present on CPU side or GPU side. Anyone? Getting it or not? Okay, so I think from my side it is the chat response is delayed. Okay, so currently when you execute this add kernel, the data will be on the GPU side, because when you execute this add kernel, the data is already transferred from host memory to device memory. That means from CPU memory to GPU memory. In simple words, you remember that whenever, let's say, you are executing a CPU code or GPU code, right? If the required data is not present on the respective memories, then page fault will occur and data will be fetched from the other's memory, right? For example, here when we executed this initialization part, during this execution, data for X and Y was residing in the host memory. But after that, we are calling a GPU function, and that function also require this X and Y variables, right? Now, when GPU try to execute or try to refer this X and Y in its own memory, it will not find that, right? So in that case, page fault will occur, and the data from host will be transferred to the device, that is X and Y variables, right? Now this X and Y variables are sitting in this device memory after execution of this add kernel. After this add kernel, now which part we are calling, which function we are calling, some fmax function is there, and that function also require this Y variable. Now this X and Y both are in the device memory, right? But now this function is getting executed on your CPU side, on CPU, right? So again, it will give page fault and data will be transferred from device to host, right? So this process is completely automated now. Earlier, before CUDA 6.0, we used to perform all these steps manually, right? We used to allocate host side variable memory, device side memory. We used to transfer, before we call this add kernel, we used to transfer this X and Y on the device side, then compute. Now again, get X and Y on CPU side using some function calls, and then call this max function, right? So these steps are manual, automated now. You just have to focus on allocate memories in CUDA malloc managed, right? Now here you can open now your Jupyter notebook, where this chapter is dedicated to understand these CUDA malloc managed function call or your unified memory concept, right? Again, very simple concept. Whatever we have discussed in this presentation now, that we just have to validate using this hands-on, right? So first of all, you will read this first paragraph, right, related to the from this first paragraph here, right, and then read this iterative optimization, okay, for 2 minutes, and then we will go for this first exercise. Yes, there is a question from, I think, Aprupa ma'am. Page fault happens at CUDA synchronize or at max calculation. So here, when we are executing CUDA device synchronize, neither CPU or GPU referring this X and Y values, right? So CUDA device synchronize is a function. It is just ensuring that CPU will wait till this add kernel finish, right? So when page fault occurs, when either CPU or GPU referring the data that is not present in its own memory. For example, here, when you execute this add kernel, which is taking input arguments as X and Y, and when you execute this add kernel, the data will be on the GPU side, right? Data will be on the GPU side when you execute. After that, you are executing CUDA device synchronize. That doesn't need any of these X and Y values. It is just a CUDA API that is ensuring that CPU is supposed to wait till the GPU complete this execution, right? Now after CUDA device synchronize, CPU, GPU function is also executed, but now X and Y, updated values of X and Y are residing in the device memory. After that, suppose again CPU is referring this variable Y. Now previously it was present on your device side, but now it will be on the host side. It is getting referred on the host side because this fmax function is normal your C function, not GPU function, right? GPU function we refer it as an with this thread and block configuration, but here we don't have this thread block configuration. That means it is a CPU function, right? Now CPU is referring it. That means it is requiring the data in its own memory, right? So that's why data will be transferred from device to host here after page fault. Fine. Okay. So now here, whenever you write any parallel program, whether it is in CUDA or any other parallel programming language, we follow this strategy, design strategy that is called as APOD. That means assess, parallelize, optimize, and deploy. Right. First of all, we are going to assess. For example, let's say I'm giving you one problem statement, right? And I'm asking you to solve or to write parallel code for this particular problem statement. Now, first of all, you will assess this problem statement. That means maybe you are going to write some sequential code for that first, maybe C program or Python program. Then you will check whether it is required to apply parallelization or not, or maybe you will try to find out which particular function in your entire application requires parallelization, right? For example, if let's say your entire problem statement it takes only 1 second to execute, then in that case it is not recommended to go for parallelization. But let's say I'm giving you problem statement or an application where you'll be having hundreds of functions, right? And you have to decide from where to start for the parallelization. In that case, we are going to perform some assessment first. Assessment means we'll try to profile your code and we'll check whether which function is taking maximum time, right? We'll check all the function times, right? We'll execute use some timer functions and we'll check how much time every function is taking, and based on that we will rank every function according to their execution time, and we'll decide which function to be parallelized, right? That is called as sequential profiling. Next, based on this logic, we'll try to apply parallelization. Maybe we'll write some parallelization code for different functions. We'll convert C functions into parallel GPU function. Then after that, again, we are going to perform optimization step. So it is not like that only in first attempt itself we'll get the optimized parallel code, right? So it is an iterative process. That means first of all we have to implement parallel code, then again check, right? Profile, you check their memory pattern, access pattern, data transfer pattern, right? Execution pattern, and you maybe after a few more iterations there is still possibility that you can even further optimize it. So it is kind of cycle, right? You parallelize, optimize. Likewise, you optimize multiple times, and finally you are going to deploy it. And that strategy is an iterative strategy, and it is referred as APOD strategy, right? So we will be following this APOD strategy in this particular chapter. So what is requirement from your side for this attending this chapter? Simple. You are supposed to must be able to write compile C++ code that you already aware of as of now. We are supposed to allocate and free unified memory that we have discussed in the previous chapter, right? We are supposed to refactor serial loops to execute in the parallel that we have discussed in the also in the previous class. Now objectives for this chapter is we'll first try to understand this Nsight system command line tool, right? This will help you to understand what is happening in the background. So as I told you in this presentation, all the things are automatically happening from host to device or device to host, right? This NSYS profiler or Nsight system profiler will help you to understand how much data is transferring from CPU to GPU, GPU to CPU, or how much time your entire application is spending on data transfer. So all those details will be made available using this Nsight system command line tool, and that is called as profiler, right? Then we'll try to understand what is streaming multiprocessor, that we already discussed when we in the first presentation what is streaming multiprocessor. Okay, most important thing is we'll try to understand this unified memory behavior and asynchronous memory prefetching. So these are the two important things we are going to understand. So these are the important things that will also help you to solve the assignment at the end of this certification. Fine. Now you just read this paragraph now. Right. So what is this ANSYS? It is Insight System Command Line tool, and that will help us to profile accelerated parallel code, right? And what information we can get from this command line tool, right? It will print the summary of output of all the GPU activities, like what are the GPU or CUDA API calls are made, right? Information about unified memory activities like data transfer from host to device or device to host, or amount of time we are spending on data transfers, host to device and device to host, right? Now we are having a simple exercise here, right? Vector addition .cu that we have discussed in the previous class, same code is there. Now only thing here is we will be trying to observe this unified memory access pattern, right? So first of all, let's go through this code first. Let's try to understand what is happening here, and then we can use this NVIDIA profiling. So first of all, we'll be having here n is initialized to 2 to the power 24. This is the left shift operator, so it will be just like 2 to the power 24. And we'll be having the size equal to n into size of float. And let's say float takes 4 bytes of memory. Now, can you tell me how much memory it is required in this case? What will be the total size here? We understood that previous example, how to find out total size here, right? So based on that, can anyone tell me how much size it will take? Simply 2 to the power 24 into 4 bytes, because these many elements we are having, right? And multiplied by 4 bytes, because every element of type float takes 4 bytes of memory. So n into 4 bytes, right? Now we are declaring these three variables a, b, and c. What we have to perform? We are supposed to perform vector addition of a plus b that will be stored into the variable c, right? So a is input array, b is also an input array, and c is an output array. So a plus b will be stored into this variable c. Now if you follow the normal C syntax, then how will you allocate memory? I will say a equal to, this is a float variable, so return type will be the float integer, float, and then malloc function, and here I will mention n into size of float, right? So this way I can allocate memory on the CPU side. But we'll be using this CUDA malloc managed function, right? So because we don't want to transfer data manually from CPU to GPU and GPU to CPU. If you allocate memory using this malloc function, the memory gets allocated only on CPU side, and we cannot refer this memory on the GPU side, right? But if you use the CUDA malloc managed function, we can allocate memory at either at CPU side or GPU side, and even we can refer it from CPU's function or maybe in the GPU function. Automatically data transfer will happen, and that is the reason we are using this CUDA malloc managed, right? So for all these three arrays, I'm going to allocate memory using CUDA malloc managed. Now you tell me till line number 63, you tell me where exactly the memory gets allocated. Can anyone tell me where memory is allocated now till line number 60? Exactly, right? So when you call this CUDA malloc managed function, as of now, memory never gets allocated, right? Why? Because maybe the compiler is thinking maybe rather than allocating now on CPU side, suppose, right? Let's say you allocate memory on the CPU side using this CUDA malloc managed, but let's say next function is a GPU function, right? Next function may be a GPU function. In that case, what will happen? You have to transfer the entire data from CPU memory to GPU memory, right? So that data transfer takes some time. So that's why when first time you call this CUDA malloc manage function, memory never gets allocated on CPU side or GPU side. Though we are saying we want to allocate memory for A, B, and C variable with size equal to this size, right? Still, memory never gets allocated. Memory gets allocated only when first time you will be referring those arrays, right? So here, after this CUDA malloc manage, first time we are referring, calling this init with function, and then we are referring it on the CPU side. Why CPU side? Because this init with function is a CPU function or C function that is will be executed on the CPU side. So first time memory gets allocated, referred from CPU side. So now when you execute this init with function and A you are passing here, now this CUDA malloc manage function will allocate memory for this variable A on CPU side. Similarly for B and CPU, because first time they are referring all these variables on CPU side. But suppose I'm having init with a kernel function, right? They're having number of threads, number of blocks and threads, right? And let's say I'm having this function 3 comma a comma n, right? If we are having this function immediately after this CUDA malloc managed, right? This function is supposed to be executed on GPU side. Now first time we are referring the variable a on GPU side, so this CUDA malloc manage function will allocate memory on the GPU side itself, right? So that is the reason when you have this CUDA malloc manage function, first time you are calling, memory never gets allocated neither on GPU side or CPU side. Fine. Now you tell me after execution of these all three statements, that is still line number 67, where exactly ABCs are A, B, and C are residing on CPU side or GPU side after line number 67. Exactly, right? Because this init with function is executed on CPU. So for all A, B, and C variables, memory gets allocated on the CPU side, right? And now we are having A, B, C are stored into the CPU RAM. Now, next thing is we'll be having this threads per block, number of blocks that we are going to decide, right? And then we are calling this add vectors into function, and that is a GPU function, right? And this is GPU function, and it is also referring the variables A, B, and C. That means three arrays A, B, and C. Now, this will result into page fault. Why? because before this function GPU function call, and this is referring this A, B, and C, the data is in the on CPU memory, right? A, B, C here, because we executed this init with function, and now GPU is referring this A, B, and C. But obviously on GPU side, A, B, C is not present, right? And that's why it will result into page fault. And when page fault is occurred, automatically this ABC variables or arrays from CPU will be transferred to the GPU, right? But though it is, we are not doing it explicitly, right? We are not doing it manually. It will happen automatically when you call this function. It is not your job now to check whether data is present on CPU side or GPU side. That will be taken care by your page migration engine to transfer the data from CPU memory to GPU memory. Fine. Now when page fault is occurred, the data for ABC will be transferred to the GPU, and GPU will complete this function execution, right? Then we are just having this checking error checking function, and after that we are having this check elements function. This function will be executed on CPU side again, right? But now data is present on the GPU side because we executed this GPU function, right? And now once GPU function is over, but still data ABC will be present, updated copy of ABC will be present on GPU side, right? And now you are referring CPU function, and which is also calling this C. Now CPU function will get page fault again, right? Here it will get page fault because it is referring C array that is currently present on the GPU side, right? And only the C array will be transferred from GPU memory to CPU memory because only C array is referred by this CPU function, right? And once you transfer that, finally after use, we are going to use CUDA free function to release the memories, right? Whatever memory we are allocated, we just want to release it. Fine. So this is the process we observed manually, right? Because you know the concept of unified memory and all those things, and this is a very simple program, right? Very short program. That's why it is possible for us to understand the data movement pattern. Now, if you are having a big project and then you want to find out this pattern, then it is quite difficult to see the step by step, right? And we are having this NVIDIA Insight system profiler. This will help to give all these details, that is profiling details, CUDA API statistics, which kernels you are executing, how much time that kernel is taking, right? Which memory operations are happening, how much memory getting transferred from CPU to GPU, GPU to CPU, how much time your program is spending on the data transfer, right? All these details we can get from this ANSYS profiler, right? And this is the exercise problem where already we have this code and we want to first of all understand this pattern. And for that, what we'll do, we'll first execute this command. This command is just giving us creating output file single thread vector add, right? If you observe here, we are going to create only one thread and one block, right? So this is just for understanding memory pattern. So that's why we have not launched optimal number of threads. We will just try to understand the data transfer pattern, right? So this output file will be created, and this output file we are going to pass to this ANSYS profile command, right? ANSYS profile command will be there, and we are mentioning stats equal to true means we want all the statistics, right? So that's why we are mentioning this ---- stats equal to true. This is the compiler, profiler flag, right? And after that, we are passing this whatever output file we have created by executing this vector add.co function, right? So first of all, execute this statement, and then we'll execute this ANSYS profiler, right? It will give some warning. You ignore those warnings message and everything. We'll just try to focus on this CUDA API statistics, how much time it is spending and how many calls are there, right? So you can see without looking entire code, you can check here this CUDA device synchronize function is you are called, and it is number of times it is called 1. Then we called this CUDA malloc manage 3 times. Then CUDA free function 3 times, right? We launched only one kernel, that's why it is 1. So you can verify here. I called CUDA malloc manage 3 times, called CUDA free 3 times, and kernel launch is 1 time. right? That information is displayed here. Then amount of time it is taken, it is mentioned here in nanoseconds. So you refer this as in nanosecond, right? So out of all these CUDA API functions, CUDA device synchronization is taking maximum time, right? So this is what we are getting the statistics about your program. So this is CUDA API statistics. Now kernel statistics. Kernel means if you are writing multiple CUDA kernels in your program, so all the kernels it will display the amount of time it is taking, right? Again, the kernel's total time is mentioned in the nanoseconds. So you just multiply 10 to the power minus 9 and then you get the time in seconds here, right? Instances will give you how many times your kernel is getting executed, right? Based on that, we'll get here number of times it is executed, right? And the name of that function you can get here, add vectors into, and this is nothing but your function prototype, right? So it is accepting 3 arguments of float, pointer, and 1 argument of integer pointer. So that is you can verify here. C, A, B are these are the arrays and N is an integer value, right? So this is related to kernel statistics. The most important here is CUDA memory operation statistics by time, right? So it is telling that 76% of the time it is data transfer is happening from CUDA unified memory H2D. H2D stands for host to device, right? Host to device means CPU to GPU, right? So that means 76% of the time it is investing on host to device transfer, right? And only 23% of the time it is transferring or investing time on device to host. Now you tell me, here it is telling that 76% time from host to device and only 23% of the time from device to host. You refer this code and you tell me why it is happening. Why host to device is more and device to host is less? Question is why it is investing more time on host to device or CPU to GPU and less on GPU to CPU. Observe this code, you will get the answer from the code itself. I will give you clue. Just check when data is transferring from host to device and device to host. Can you tell me line number where data is transferring from host to device or CPU to GPU? Exactly, right? Karthik, you are saying number of variables or array transfer from GPU to CPU is less because you can see here when data is getting transferred from CPU to GPU for this function, right? GPU function, we are transferring C, A, and B, all the 3 arrays, right? But when data is transferring from GPU to CPU, we are requiring only C array, right? So that's why here the most of the time it is spent on your data transfer from host to device, right? And this will tell you number of pages you are transferring, right? Here the number of operations you are performing, that is, and the time is again in nanoseconds here. Then if you want to see how much data is getting transferred in kilobytes, then you can get here that information from here. So you can see again 39 or 393 megabytes of data is transferred from host to device and 31 megabytes of data is transferred from device to host. And you can verify here it is 3 times more, right? Because we are transferring 3 arrays from host to device and only 1 array from device to host. Fine. So these are the statistics we are getting. These are the runtime statistics that are not that much important in this context, right? So you can skip this, right? Fine. So I hope you got the clear idea about what this profiler is giving information to us. Any doubt till this point? Yes, yes, you are right. At line number 83, we are transferring data from CPU to GPU. Right? Now, next exercise we are having is optimize and profile. Now, question here is mentioned. If you read, we have to update this vector addition code, its execution configuration, so that it runs on many threads in a single thread block. Right? We want to execute on many threads. Right? Again, we try to compare this output. How much time it is taking? It is taking these many nanoseconds. Now we will try to launch multiple threads here. So as of now, only one thread block is there, and we are having only one thread. So I'll just update it to 1024. Right? So now we'll be having 1024 threads in total. Right? Then let's execute here. And now you can see overall time is reduced here, right? So earlier it used to take these many nanoseconds, right? So 1 2 3 4 5 6 7 8 9, so 2.2 seconds or 2.3 seconds here earlier with one thread, and now it is 1 2 3 4 5 6 7 0.1 second, right? So earlier it was taking 2.3 seconds, and now it is taking zero point 0.1 second. Can you tell me what is the speed up or how much improvement we got here? Uh, what do you mean by variable n? Variable n is nothing but the size of your input, right? How many data points are there in variable A, variable B, and variable C, right? So n stand for number of elements in your array. Now my question is, what is the speed up you achieved? How will you calculate speed up? So with one thread, it is taking time 2.3 seconds, right? And with 1024 threads, it is taking time is 0.14 second, right? My question is, what is the speed up that we achieved here? Yes, speed up is nothing but sequential time by parallel time. Sequential time is 2.3 divided by 0.15. So what will be the answer? 2.3 divided by 0.15. Simply 2.3 divided by 0.15, right? So it is giving you 15 times better performance when you just create 1024 threads, right? So that we can observe here. Fine. So this is how we can profile our code and we can get this entire information. Exactly. So everybody is correct here. Just give me a second. For me, your chat response is a bit delayed, so I'll switch my network.
Sir, you're muted.
Oh, I'm sorry. So let's go to the next exercise, that is optimize iteratively. You read these all instructions first, then we'll try to modify accordingly. Fine. So what they're expecting, we want to modify this execution configuration, right? So let's open this code and we just want to modify, right? So as of now, only 1024 threads are there. Maybe we can convert how many data points we are having, 2 to the power 24, right? Let's say I'll make, sorry, I was supposed to be making 1024 here, and number of blocks equal to 34, right? So let's see whether we can get any performance improvement or not, right? We can see again performance is further improved to 0.13, right? So that means once we go on increasing number of threads as per your data size, we can expect better performance, right? Right, so it is around 0.112 second now, right? So as per your data size, we can increase number of threads and we can expect the performance even improved further, right? So using this profiling, you can see rest of the results will be same, that is how much data transfer is happening and everything. Slightly we can say that there may be difference, but almost we can see approximately same results for data transfer and amount of time it is spending on the data. Only thing we are modifying is this execution configuration, that means how many threads we want, and based on that, as number of threads are getting increased, your overall time is decreasing. Fine. Any doubt till this point? Take few seconds again, go through, try to execute all these programs, try to modify this configuration, right? And observe the results. Yes, Karthik, I'm not getting your doubt. Can you please elaborate?
Sir, can you hear me?
Narayana, what you're asking, will we get the code means? I'm not getting your doubt. Yeah, all the codes and everything you can download. I think you can, if you go on this open, right? So from here you can download all these whatever codes are there, right? From here also, or maybe if you want to download from here also, I think you can download. So whatever codes you want to download, that it is okay. Okay, the codes I have written. But again, the codes, you also are having the similar codes, right? I'm just modifying those. So parallelly, you can modify and you can download those. But rather than only following my way of modification, you can attempt by yourself, right? You try to practice. Maybe I created here 256 threads. Maybe you create here 128 number of blocks. Likewise, you try to change this configuration and observe the performance difference. That's it, right? I'm just giving you one of the possibility to increase. So there are many possibilities to design this thread configuration and block configuration. Fine. Okay. Any doubt till this point? We'll continue for 10 more minutes and then we will be having break. Okay, so if there is no doubt, so let's continue with the new topic, that is streaming multiprocessor, right? So in the first presentation, I told you what is streaming multiprocessor. It is just group of GPU or CUDA cores, right? So we'll be having GPU, right, which is having multiple streaming multiprocessors, or it is abbreviated as SMs, right? And in every streaming multiprocessor, we'll be having number of CUDA cores, right? So in the previous architecture, we have seen either we can have 64 number of cores that consist of creates one streaming multiprocessor, or maybe in recent GPU architectures will be having one streaming multiprocessor which may have a 128 number of cores, right? So it is just a way to organize your thousands of cores on the GPU side. It is not like that. If I'm having 5,000 number of cores, so it is not in the stored designed into a single array of 5,000 cores. So it will be combined to form streaming multiprocessors, and every streaming multiprocessor will be having number of cores like 32, 64, 128, and so on, right? Now, based on this streaming multiprocessor, also we can get performance improvement, right? So typically, there is an empirical study that we want to ensure that all streaming multiprocessor must be utilized properly, right? For example, let's say I'm having here 1, 2, 3, 4, 5, 6, 7, 8, 16 number of streaming multiprocessors are there, and I'm launching 24 number of blocks, and every block is having 4 number of threads, right? So 16 number of streaming multiprocessors are there, and we are launching 24 number of blocks to let's say to execute any function, and every block is having 4 number of threads, right? So when you design this configuration, so all these blocks will be scheduled on streaming multiprocessors, right? So out of 24, 16 blocks will get scheduled on 16 streaming multiprocessors here, right? And next 8 blocks will be scheduled later, right? So this is how the blocks will be scheduled on this GPU, right? Now, why it is important? Because you can see here, while we are executing the next 8 blocks, here we'll be having these remaining 8 streaming multiprocessors are sitting idle, right? That is not going to utilize this streaming multiprocessor at 100%, right? So only 50% of the streaming multiprocessors are utilized after executing of this first 16 blocks, right? But what we want to ensure that maximum utilization of your streaming multiprocessor. So what we can do to ensure that the 100% utilization of the streaming multiprocessor, we will launch number of blocks that are multiple of this streaming multiprocessor, number of streaming multiprocessor. right? So rather than launching 24 number of blocks, either I can launch 16 blocks or 32 blocks, right? So if you ensure that 16 or 32 blocks, so it will ensure that 100% utilization of this streaming multiprocessor, right? So this way we can improve the performance further, right? But again, you may not observe very drastic performance improvement, right? When you say your number of blocks are exact multiple of your number of streaming multiprocessors, but still you'll find out this typically if you are working on very big project or very computationally intensive job, then you might observe the difference, execution difference, when you are having blocks that are not multiple of streaming multiprocessor and the configuration where number of blocks are exact multiple of streaming multiprocessor. Whatever exercise problem we are discussing here in this chapter, where we are not using very computationally intensive jobs, simple vector addition program we are working on. So that's why you may not get the performance improvement better. But definitely if you're working on big project, you will get this kind of, you will see the performance difference when you are having a number of blocks that you are launching that are exact multiple of number of streaming multiprocessors, right? So this is one of the advanced technique to optimize your code further, okay? Now there is a advanced concept that is called as warp, means uh, here whenever you launch any block, any thread block, right, we can provide any configuration, right? I can say I want to launch one block, maybe 50 threads, that is also possible, right? I can say maybe two blocks with 25 threads, right? So likewise we can give any configuration, right, as per your data size. But it is recommended that your number of threads per block is supposed to be multiple of 32, right? So your number of thread blocks is supposed to be multiple of 32 in order to get better performance or maximum performance, right? Why it is recommended? Because on GPU, it will not execute one thread at a time. It will execute a group of 32 threads at a time, and this group of 32 threads is referred as warp, right? So if you are familiar with, let's say, CPU scheduling, in CPU scheduling, the CPU schedules one process at a time, right? So for example, I'm having this Firefox browser is there, MS Team application is there, I opened this Notepad application, then PDF viewer is there, right? So all these applications I'm executing, right? No, sorry, I opened this all these applications and CPU is executing all this application. But CPU, if I'm having only one processor or one core, CPU will schedule one process at a time, right? Because I'm having only one computing resource. On GPU, you will be having thousands of cores, right? And if you are having thousands of cores in GPU, it will not schedule one thread at a time. It will schedule a group of 32 threads at a time, right? And if we are having this thread block configuration, like a thread number of threads per block is of multiple of 32, then it will reduce overheads and you will get maximum performance, right? So that is called as warps. So key takeaway from these points is, if you want to get better performance, first of all, ensure that number of blocks that you are going to launch is exact multiple of streaming multiprocessors. That is one optimization technique. And again, this is, you just have to follow it blindly. You don't have to prove it some mathematically, or you don't have to give any proof for that. You just follow it blindly, because as per the scheduling policy on GPU, right, this is the optimal way to decide number of blocks, right? Second optimization technique is, whenever you are having number of threads per block, it is supposed to be multiple of 32 threads, then you will get maximum benefit, right? So these 2 points you remember when you will be designing or configuring your threads and blocks. Fine, but you may ask how to find out number of streaming multiprocessors in your GPU, because it is possible that maybe in future we'll be having new generation of GPUs, or maybe everybody is having different set of GPU, and on different set of GPUs maybe there are different number of streaming multiprocessors. Then how to find out the number of streaming multiprocessors? And to do that, very simple function that we can execute on in your existing CUDA program to find out number of streaming multiprocessor, right? So all these properties of your GPU will be stored into a function that is called as CUDA device properties, right? And whenever you install CUDA toolkit in your local system, in its bin folder, lib folder, you will find out a program that is called as device query. And when you execute that device query, you will get all the details about your GPU, right? So as of now, let's execute this program, that is CUDA device query. Here we are not writing any GPU code, we are just executing the CUDA device query function. So I'll copy paste the solution as it is, and we will execute to find out the details. So it is saying that device ID is 0, meaning is that I'm having only one GPU and which ID is 0. Number of streaming multiprocessors equal to 40, and these are the major and minor version of this GPU. That is, major version is 7, minor is 5, and warp size is 32. Right? For the GPU, number of SMs equal to 40 and warp size equal to 32. So what is your optimization strategy here? Whenever you are deciding number of blocks, it is supposed to be multiple of 40 to ensure maximum resource utilization or streaming multiprocessor utilization. And when we are having warp size equal to 32 means we have to decide thread block size, it is supposed to be multiple of 32. So I can have maybe 32 threads per block, or 64 threads per block, or 96, or 128, 256, and so on. Right? So whenever you are deciding block size, don't randomly say that 100, 101, right? 32, 50, likewise. So always ensure that your block size is supposed to be multiple of 32, and number of blocks is supposed to be multiple of 40. Fine. Any doubt till this point? So this strategy can be very useful when you will be working on coding some assignment problems in coding round, because even if you miss by, let's say, 1 second or 2 seconds, right? Because everybody is going to submit their assignment timings, and in case, let's say, top 3 ranking are like that, one is taking 1.1 second, other is taking 1.2 second, somebody is taking 1.5 second, then obviously the difference between is only 0.1 or 0.2 seconds, right? But it is possible that you are getting this kind of performance difference because your thread and block configuration is not well optimized, right? So for that reason, you are supposed to pay attention, follow these optimization guidelines also, right? Maybe you implement parallel version very efficiently, but your thread and block configuration is not proper. Then maybe there is a 2-3 seconds difference is there. Both codes are same. Only difference is the thread and block configuration. Then in that case, you may lose your rank in the final submission. Fine. Okay. So let's have break here for 10 minutes. Okay. And then after 10 minutes, we'll continue with our this next topic, that is unified memory migration and asynchronous memory prefetching, right? Meanwhile, if you have any query, you can ask. I'll be here only. Those who want to take break, you can come back at 11. Fine. Any doubt till this point? Okay, so the previous code that I executed here, sorry, here I copied the solution I copied into that main program device properties.cu. I copied it and then executed it. That's why there is no error. Otherwise, they are asking us to modify according to this CUDA get device ID, device property, etc. into that code, right? So don't directly run it. You open the solution, copy the solution code, and paste it into the get device property.cu program, right? Then you execute next statement, and then you'll get all these details. Fine. I'm not discussing anything. I'm just checking the course. Okay, so let's start now. Now you got to know that the behavior of unified memory, right? So we have the similar presentation here to understand the behavior of this unified memory. The same way we describe using this presentation. Here we try to understand by detailed program. Okay. So now there is an exercise on unified memory migration and page faulting, right? Again, very simple exercise. First of all, open this code pagefaults.cu, and here they have mentioned a main function, and inside the main function n is declared and a variable a is allocated with memory using CUDA malloc managed, right? Now here some instructions are mentioned. You have to first of all hypothesize the behavior of the code. Meaning is that first of all they are asking us what will happen, right, when unified memory is only accessed by GPU, right? Here we are allocated memory using CUDA malloc managed. Now what if memory gets accessed by only GPU, whether there will be any page fault or not, right? So let's say after this CUDA malloc manage memory function, I'm calling this device kernel, right? That means we are referring this device kernel, and here I will mention only 1, 1. This is sample here, and I'll pass a here, right? So device kernel is taking a comma n. Now question is, if after this CUDA malloc managed only the GPU function is there, whether there will be page fault or not. So can you tell me whether there will be page fault or not in this case? Question is, after CUDA malloc managed, whether it will result, if you call this device kernel, whether it will result into page faults or not, right? So you can see here, there is no statistics of data transfer, right? Page fault is there, initially it is when we call, but there is no evidence of data transfer. Why? Because when you call CUDA malloc managed, right, memory never gets allocated on CPU or GPU. First time we are referring from device kernel, so immediately the memory gets allocated on GPU side for variable A, right? Page fault will be there, but no data transfer is there, and that's why you can see here there is no evidence of the statistics in case of this NSID profiler of data transfer from CPU to GPU or GPU to CPU. Fine. That is the first question. Next question, what happens when unified memory is accessed only by CPU? So I'll comment this code, function, and I will call now host function. I will call host function a comma n. Now question is, what happens when unified memory is accessed only by CPU? Whether there will be page fault or data transfer? Data transfer will be there or not? No, because page fault will be there, but there won't be any data transfer. So let's again compare, execute, save this program. Every time we are modifying, press Ctrl S and save this program, come back and execute these two cells. Right? So you can see there won't be any data transfer statistics here. Right? Only we'll be having CUDA malloc managed and CUDA free. Right? We don't even have kernel launch or GPU function execution, so that statistics is also not present in this profiling output. Right? So this was the second question. Now third question is, what happens when unified memory is accessed first by GPU then by CPU, right? That means unified memory first here we are calling device kernel function and followed by that host function. That means GPU first and then CPU. Now what will be your answer? Whether there will be page fault or not? First question, and whether there will be data transfer or not? That is second question. What will be your answer? Think on it. Unified memory is allocated. Now you're calling GPU function first, that is device kernel, and followed by that host function. Right. Page fault will be there two times because device kernel is accessing first time. So there will be page fault. And after that, host function is also calling, there will be page fault. And data transfer will be there from CPU to GPU or GPU to CPU. Yes, exactly. Yes. The data transfer will be there from GPU to CPU. So let's verify that. Okay. Right. So we can see here the maximum data transfer is from, host to device. Do we have any function call? Yes, you can see here now maximum data transfer will be from device to host, right? Then you can see the device kernel time also, that is this much nanosecond. Okay. And the last question is what happens when accessed first by CPU and then by GPU. So we'll just change this order. We'll access first by CPU, then by GPU. Again, there will be page fault, right? And now data transfer is supposed to be from host to device. Right? We can have data transfer from host to device here. Fine. Let's execute one more command here to check. Yeah, fine. Right? So this is how we can hypothesize first the unified memory behavior. Okay. So these are the 4 questions asked, but they asked us to first of all hypothesize what will be the output and then cross verify. We try to guess, and whatever our understanding is there, that is reflected in your profiler output. Okay, fine. So this is about your exercise on explore unified memory migration and the page fault. Any doubt till this point? You practice it for a few minutes, all these questions. Fine. Now let's revisit our vector addition code here. Now what is expected in this? We have to optimize this data transfer pattern in this case, right? So first of all, let's profile your basic vector addition code that is already present provided here, right? Now first of all, we have to observe this pattern and we have to hypothesize about how data transfer will happen, and we wanted to optimize this. Okay, I think we are supposed to execute that first. Uh, okay. So before we jump to that vector addition, first of all, make sure that we are going to execute these 2 cells from the exercise optimize vector add with grid size to number of SMs, right? So you do that, execute first, because this output file is required to perform the profiling, right? SM optimized vector addition. So you go to this exercise back. Okay, I will execute this again, and you'll see it is printing all the details, right? As of now, you can see the details like add vectors into kernel, which is taking 0.13 second, and there are data transfer from host to device and device to host, right? Host to device, 393 megabytes is transferred. From device to host, 131 megabytes is transferred. Now we want to optimize this data transfer, because you can see here even data transfer is also taking some time, right? And to compare to your execution also, it is quite significant, right? Amount of data is transferred or amount of time spent on data transfer, right? Now what is expected in this? We want to optimize this behavior, right? First of all, let's try to understand what is happening in this code. Open this vector add.cu. Okay, so go to main function. Here we declared 3 arrays, right? We allocated memory using CUDA malloc managed. Then we are calling init with function on CPU, right? After CPU function execution, we are calling GPU function, and after GPU function, we are calling CPU function, right? So what is the pattern here? We allocated memory first, right? After memory allocation, we are calling CPU function, then GPU function, and then again CPU. So this is the calling pattern. CPU function initializing. For initialization, we are using the CPU function, right? After initialization is done, then we are calling addition function that is executed on GPU, that is GPU function. And after that, we are checking whether results are correct or not using CPU function, right? So if you see, the data transfer will happen in this region when we are shifting from CPU to GPU function and from GPU to CPU function, right? So here when we are going from CPU to GPU function, data transfer will be there from host to device, H to D. And when we call a CPU function after GPU, then data transfer will be from device to host, right? Got this sequence? Now they're asking us to optimize this code, because if you see, we are calling first init function, right? When we call this init function on CPU, here memory gets allocated. At this point, memory gets allocated on CPU side. Then we are calling GPU function, that is add vectors into. Then data will be transferred from host to device. All 3 arrays A, B, C will be transferred from host to device. Now on GPU, we will execute this add vectors into function. Then after we want to transfer this C variable or C array from device to host, right? So here C array will be transferred, and we are using this check element function on CPU. Only C will be transferred from device to host. So this is the whole sequence of execution. Now, by looking at this, can you tell me any way to avoid this kind of data transfer? Or maybe is it possible to reduce any of this data transfer, host to device or device to host? If so, how will you be able to manage that? Think on it. Solution is very simple. You observe this code first and this pattern, right? Observe this code. The pattern is CPU function followed by GPU, then CPU. And we are switching from CPU to GPU function. We are having host to device data transfer, and from GPU to CPU, device to host data transfer is there. My question is there any way we can avoid any of this data transfer? That is first question. If so, how? Anyone? Answer is very simple. Think on it. Question is, now we are transferring data after this init function. For example, if you go from the first line here, first of all we are allocating memory, then we are using CPU function. Here page fault will occur. After CPU function we are having GPU function. When we execute CPU function, the data memory gets allocated on the CPU side. Immediately after that we are having GPU function, so it will cause this data from transfer from host to device, because after CPU function we are calling GPU function and both are working on same data. So it will cause data transfer from host to device for A, B and C arrays, right? When we go from init function to add vectors. After add vectors into function, we are calling check element function that is requiring C variable. So when we are executing this add vectors into, data is present on the GPU side. A, B, C variables are present on the GPU side. Now after that we are calling CPU function that requires C variable. So data transfer will happen from device to host or GPU to CPU for only array C. Right? This is the flow. My question is there any way we can avoid this, any one of this data transfer, right? If it is possible, how we can avoid that data transfer? Exactly, right? Subhradweep and Vinayak, both are, you are correct, right? So here we are calling this init function on the CPU side. So that's the reason memory gets allocated on the CPU side. Then we are calling GPU function. So that's why your data transferring from CPU memory to GPU memory. But what if we can convert this init with function itself is a GPU function? Then what will happen? The memory gets allocated for A, B and C on GPU itself. Then add vectors into function will be called after that. And for this add vectors into, these A, B, C variables will be already present on the GPU side. So there will not be any data transfer, right? And finally, after that, we are calling check element function. And for that, only one array need to be transferred. So we can avoid completely this data transfer if you can manage to convert this init with function into a GPU function, right? So how we can manage that now? It is very simple. Just we have to convert this into a GPU function. So what will be your first step to convert into GPU function? First, we are going to write a global keyword, right? Then we will have this thread configuration. I will use same threads and block configuration for init with function also. So I'll copy paste this threads and block here, and we will mention here same threads and block configuration, right? So now this init with function calling is changed to GPU function call, and this function definition we converted into GPU, right? So here we just need to add this statement, create a global ID, and if index is less than n, we will execute this. Sorry, we also need to go for this slide, I guess. Right? So this is how we converted your CPU function into GPU function. Hopefully it is supposed to execute without any error. Where we are supposed to execute. Yes. Okay, there is an error. I is uninitialized. Right now you can see previously we had host to device and device to host data transfer. Right now we are having only device to host data transfer. We completely removed that host to device data transfer. Right. So if you want, I think the solution is perhaps already present somewhere. Okay, here I think. Yeah, you can find out solution also here init with function. They are converted into GPU functions, right? So you refer that solution also and try to execute that. Fine. Take few minutes and try to attempt that also. Try to convert all this function manually rather than copy pasting from the solution, so that you'll get clear idea about how to convert a CPU function into GPU function also. Okay. Any doubt till this point? Feel free to ask. You can start your mic also, even if you're not getting any simple topic also. Any doubt till this point? Okay, so a final topic that is left from this chapter is asynchronous memory prefetching. right? So if you know, let's say in advance data transfer, right? For example, if I open this vector add.cu, just a second. Okay, so for example, if you refer this code vector addition.cu, here you know in advance that data is required in this case for the, after this init with function, sorry, after this add vectors into function, data is already required on the CPU side for array C, right? So if you don't use any asynchronous prefetching, what will happen? For this C array, first of all, it will be entire array will be divided into number of pages, right? And it is not like that. When you are referring, the entire array will be transferred from GPU to CPU, right? For example, let's say on CPU I am referring C of 0. So the entire array is divided into number of pages. Maybe every page is having, let's say, 100 elements, right? And C of 0 is present in, let's say, this page. So only this page will be transferred from GPU to CPU. It will not transfer all the remaining data points, all the remaining pages, right? I repeat here, your C array will be divided into number of pages, right? Now all these pages are present on GPU memory, right? And let's say on CPU, you are only referring C of 0. So in that case, the data, entire data for C will not be transferred from GPU to CPU. Only the page which is having C of 0 will be transferred from GPU to CPU, right? For example, let's say C of 0 is somewhere here in the first page. Now only first page will be transferred from GPU to CPU, right? So typically what is the overhead here? First of all, we have to divide entire data into entire array into number of pages. We have to keep track of which particular value is present in which particular page. Then whenever it is required, only that page will be transferred by the page migration engine from CPU to GPU or GPU to CPU, right? So this incurs one extra cost, right? It induce one extra cost or overhead to manage all those things, right? So it is better when we'll be having a random access. That means you don't need complete array, right? And you need only few elements of this array to be transferred from GPU to CPU. In that case, this unified memory strategy is better because rather than transferring entire array, you are just transferring few pages, and transferring few pages takes less time compared to transferring the all entire array, right? But in our case, we know already we want from GPU to CPU complete C array to be transferred from GPU to CPU. Then why to invest the time on dividing the entire array into number of pages, right? Then again maintaining the which particular array element stored in which page. So all these things will induce extra cost here, right? Overhead here, right? But let's say in advance, you already know that entire array is required, not only few elements. Then in that case, we use this CUDA memory prefetch async function, right? Or prefetch technique. So CUDA memory prefetch async function, which will transfer the entire data from GPU to CPU, right? Or CPU to GPU, rather than making your paging and everything. So it will transfer the entire larger chunk, right, in one go only, rather than dividing it and transferring one page at a time, right? So what is the advantage of unified memory? If we are having sporadic access or random access for only few elements of this array, right? Only let's say C of 0 or C of 100 is required. Only that page will be transferred, and you don't have to worry about transferring rest of the array elements, right? That is optimized way. But in our case, after this GPU function, the entire array C is required on CPU side to check whether the output is correct or not, right? So in that case, we can avoid these overheads of creating pages and chunk divided into chunks and etc., right? Rather than transferring one page at a time, we can transfer this complete chunk in one go without making this pages and partitions, right? And that is allowed using this CUDA mem prefetch async function, right? So how it works? We are having this CUDA mem prefetch async function. We are having here pointer to some unified memory data, right? Whatever, whether it is a C, A, or B, whatever array is there. And here we are mentioning size. That means how much data you want to transfer, and device ID. Device ID means your GPU ID. In our case, we are having only one GPU, so device ID will be 0 here, right? So this function help you to transfer entire array from GPU to CPU in one chunk only, rather than dividing into number of pages, right? So this is allowed using CUDA mem prefetch async function. Same we can do for transferring data from CPU to GPU, right? So in that case, what we can do, pointer again to that data size, and we can provide the CPU device ID. This is again one variable which will give you the host ID or CPU ID, right? So this is the purpose of this CUDA prefetch async. And in this assignment or exercise, what it is expected, you are supposed to modify this code again, so that we can use this CUDA mem prefetch async, right? So where you can apply that CUDA mem prefetch async in this code. So here we are having init malloc memory malloc allocation is there. This is GPU functions are there. Again, we are having GPU function. Then we are having CPU function. So where it is the appropriate position to apply this CUDA mem prefetch async? Where do you think you can apply this CUDA mem prefetch async function? Before GPU function, but okay, it is supposed to be after GPU, right? Because here we are having init with function, right? No, yeah, before CPU function, right? So here there is no data transfer is there, right? Because memory gets allocated on GPU side. After that we are having GPU function, so there is again no data transfer, right? Now we are having this check element function which requires this entire array C, right? So we can add this CUDA mem prefetch async function before this CPU function, and we can transfer this entire C array from GPU to CPU, right? So this we can perform using, you can refer this solution. So you can see here they are using okay, so what they are doing, first of all transferring here, but we can also transfer from GPU to CPU also, right? Only thing, sorry, not here, it is supposed to be above this, right? So here instead of device ID, you can write to the CPU device ID, right? So C array will be transferred from GPU to CPU, and then we are using this check element function. Fine. So this is how we are supposed to optimize your memory behavior also, right? So not when you're writing CUDA program or any parallel program, it is not like that every time you are making a code parallel only, right? You are writing a CUDA functions, parallel CUDA functions. Sometimes your performance is dominated by the data transfer, right? So in that case, we have to effectively transfer this data from CPU to GPU or GPU to CPU, so that overall performance will be optimized. Fine. So this is all from your chapter number 2, right? And we have discussed what is Nsight command line tool, what is streaming multi-processor concept, right? What will be the optimal number of thread blocks, optimal number of threads per block that we have discussed. We understood the unified memory behavior, right? And finally, asynchronous memory prefetching. Now there is a final exercise problem is there where you have to accelerate or optimize this function that is saxpy. And again, you will see the details of this function is like ax plus b, right? So that is multiplication, right? You try for that whatever the techniques that we understood from this chapter and previous chapter, you try to apply that, right? And you go for this exercise problem. If you stuck at any point, you can get the solution here also. You can see the solution, right? And practice this assignment. Fine. Okay. So if you have any query till this point or go through first two chapters, if you have any doubt in any of the chapter, right, you can ask. We have still 15 minutes time to revise all your concepts. And if you have any doubt, you can discuss. At 12 o'clock, we'll be having lunch break. By the way, I was expecting at least few of teams, they will try to complete this certification by yesterday night itself, right? Because all the topics are self-explanatory. You can read the context, read the presentation files, and you can practice immediately by modifying the codes, and you can understand everything, right? I was expecting that at least one or two teams, they will try to complete this course by yesterday night itself. Yes, any doubt till this point? If you have any question, any query, you can start, open your mic and you can discuss. Try to clear all your doubt as many as possible during the live sessions only, because once live sessions are over, then all the events mostly will be in offline mode. So we'll be providing your problem statement, then you have to work on those problem statement by yourself, right? Even if it is very stupid doubt or very silly doubt is there, don't worry, you just ask. I'll try to explain one more time, maybe in the different way. Just to give quick recap, in the first, we understood what is GPU architecture, right? How it is different from CPU architecture. Then we tried to understand what is GPU configuration using NVIDIA SMI command. We understood thread and block configuration, right? Then unified memory behavior, what is streaming multiprocessor, right? Then ANSYS profiler that we have discussed. In previous class, we have seen this malloc managed function. We tried to write different kernels with different threads and block configuration, right? We tried to parallelize for loop, right? And now we have discussed this advanced topic like unified memory and ANSYS profiler. In the next chapter, after lunch, we'll be discussing about again advanced concept in CUDA programming, that is streaming, that will help us to even improve the performance further. Right, CUDA streams is there, and followed by that, immediately we'll be having one project assignment in the third chapter, and again very simple assignment. You just have to apply whatever concept we have discussed in the first and second chapter itself, right? So immediately after you get solution, the certificate will be generated, and we will provide all the instructions how to you are supposed to submit the certificates, right? In your course page here, in progress, I think you'll find out that survey or feedback link somewhere in progress. At the end of every certification, you are supposed to submit two things: the generated certificate, digital certificate, and that is for all your teammates. So if you are having 4 teammates, then for all teammates you are supposed to send the certificate plus the screenshot of feedback that you have submitted here, right? I think when you click on next after the chapter number 3, they will ask you to this kind of course survey, or some questions will be there, right? In my case, the questions are quite different because I'm an instructor, but in your case, I think they will uh, ask feedback about this training session, right? So you are supposed to submit those, and you have to take screenshot of that submitted before submission of that, right? And you have to share the screenshot over email. We'll see maybe in the next session, we'll provide all the details how you are supposed to submit your certificates and feedback. So you don't have to write 2 different mails. Only one mail is enough with your for one team, and only team lead is supposed to submit all certificates and the feedbacks for all by the all participants. Okay, so if there is no doubt, can we take lunch break now then, if there is no doubt? Yes, anyone? Okay, then I think we can take lunch break now.